Hello guys, this is Srinivasrao Peruri, math educator. Yes, today I am going to explain group 2. Groups beta. This topic is very important for degree students, right? So here, most important question. This one is very important here. Show that a non-empty subset H of a group G is a subgroup of G. If and only if IFF means okay. If and only if that is necessary under sufficient condition. AB inverse belongs to H for all A comma B belongs to H. This is the question. Long answer question, very important. Right? So now here, given that H is a non-empty subset of a group G. Yeah. Now necessary condition. Okay, right. Suppose we have H is a subgroup of G, then we have to show that okay, for all A comma B belongs to H such that AB inverse belongs to H. I repeat, suppose necessary condition, suppose we have H is a subgroup of G. Yes, look at this necessary condition. Necessary condition. Yes, suppose we have H is a subgroup of G. H is subgroup of G. Then we have to show that right for all A comma B belongs to H such that yes, AB inverse belongs to H. That's it. Understood? This is the necessary condition. Right? Suppose we have H is a subgroup of G, then we have to show that for all A comma B belongs to H such that AB inverse belongs to H. So, given that H is yes a subgroup of G. Subgroup of G means H itself is a group. Understood? That implies H itself is a group. Itself is a group. Okay. Group means closure property. H satisfies closure property, associative property, identity property, inverse property. 4 properties are satisfied. Right? H itself is a group. By using the group definition, we have to show that AB inverse belongs to H. Understood? Yeah. Now listen better. Yes, by the inverse property, yes, for all, yes, A belongs to H, there exists unique. Yes, A inverse belongs to H such that A into A inverse often belongs to H. Understood? By the inverse property, for all A belongs to H, there exists unique A inverse belongs to H such that A into A inverse belongs to H. Right? That is equal to inverse property this one. Right? So here, given that H is a subgroup of G, that implies H itself is a group. Okay, right? Actually, this one is also no need this one. Understood? So, simple property is H itself is a group. So, this implies, yes, A comma B belongs to H, okay, such that AB belongs to H. Understood? By the closure property, since H is a group. Okay. Now, next one is A comma B belongs to H, which implies A comma B inverse is also belongs to H. Okay, every element in H has a unique inverse. That's why A comma B belongs to H, which implies A comma B inverse belongs to H. That implies A into B inverse is also belongs to H. Since by the closure property, H is a group. Bus completed. So necessary condition means suppose we have H is a subgroup of G, then we have to show that for all A comma B belongs to H such that AB inverse belongs to H. Right. So H is a subgroup of G. That implies H itself is a group. Group means, according to the definition of the group, yes, H satisfies closure property, associative property, identity property, and inverse property. So, by using the closure property, yes, A comma B belongs to H, which implies A into B belongs to H. So, how can you say that binary operation is multiplication according to the data? So, look at this, A into B. A into B inverse belongs to H. That's why indirectly dot is a binary operation. So here A comma B belongs to H, which implies A comma B inverse belongs to H. That implies A into B inverse belongs to H. Yes, necessary condition over. Now sufficient condition below. Yeah. Now sufficient condition. Sufficient condition. What the sufficient condition? Suppose we have, right? Yes. For all H is a non-empty subset H of a group G. Okay. Then for all A comma B belongs such that A B inverse belongs to it, then we have to show that H is a subgroup of G. I repeat. Yes. Suppose we have yes, A comma B belongs to H. A B inverse belongs to H for all A comma B belongs to H. Then we have to show that H is subgroup of G. Understood? Yes. Sufficient can suppose we have A B inverse belongs to H. Simple condition below. Suppose we have A B inverse belongs to H for all A comma B belongs. Then we have to show that H is a subgroup of G. Subgroup means indirect. In order to we have to show that H is a group. Okay. In order to we have to show that. In order to we have to show that. Okay. H is a group. H is a group. Group properties are, first one is closure property, okay, right? Associative property, identity property, inverse property, right? These four properties are there. So here, in order to be have to show that H is a group. First one is in this case, yes, identity property. Identity, next inverse, next closure property, next one is associative property. Right. So first one is yeah, here A comma B belongs to H, which implies AB inverse belongs to H. By using this property, we have to show that H is a group. Understood? So I repeat that one. This one is A comma A belongs to H, which implies A into A inverse belongs to H. A into A inverse belongs to H. So this is equal to, this implies, yeah, E belongs to H. E belongs to H. Understood? So, identity property over. Identity property over. Right, brother? A into A inverse is equal to E belongs to H. So, A comma B belongs to H, which implies AB inverse belongs to H. So, A comma A belongs to H, which implies A into A inverse belongs to H. That implies E belongs to H. So, identity property over. Now next one is, second one is, yeah, inverse property. Okay, right. So we have, yes, A comma B belongs to H, okay, which implies AB inverse belongs to H. That implies, yeah. Now next one is, right, E belongs to H, comma, A belongs to H, which implies, right, E into, this one is E into A inverse belongs to H. Understood? We have A comma B belongs to H, which implies A B inverse belongs to H. So that implies E belongs to H, A is equal to E, I consider that. Okay, B is equal to A. E belongs to H, comma A belongs to H, which implies E into A inverse belongs to H. That implies this one is equal to A inverse belongs to H. Since okay, E into A inverse is equal to A inverse. Suppose that multiplicate identity is 1. 1 into A inverse is equal to A inverse. That's it. So inverse property over. Now next one is, the third one is, yes, closure property. So look at this, A comma B belongs to H, which implies, yes, AB inverse belongs to H. Right. Now, so A comma B inverse belongs to H, which implies A into B inverse whole inverse belongs to H. That's it. What is the closure property? A comma B belongs to H, which implies AB belongs to H. Yeah. Now this implies A into B belongs to H. Therefore, H is closed. Therefore, H is closed under multiplication. Under multiplication. Okay, guys. Now associative property. Associative property. Yes. So H is already closed, no? So A comma B comma C belongs to H such that, yes, AB into C is equal to A into BC. Right? Associative property. So here, okay, right? Theorem is completed. Now look at the board. Show that a non-empty subset H of a group G is a subgroup of G if and only AB inverse belongs to H for all A comma B belongs to H. Okay, right. So here first one is, yes, given that H is a non-empty subset of a group G. H is a non-empty subset of a group G. Necessary condition is, suppose we have H is a subgroup of G, then we have to show that A comma B belongs to H such that AB inverse belongs to H. That's it. So here, given that H is a subgroup of G, subgroup means is nothing but group. Okay. Group means H satisfies closure property, associative property, identity property, and inverse property. So here A comma B belongs to H, which implies AB belongs to H, since H is a group. That means, okay, closure property. Right. Similarly, A comma B belongs to H, which implies A comma B inverse belongs to H. Every element in H has a multiplicative inverse. That's why, so B belongs to H means B inverse also belongs to H. Sir, why are not taking A inverse belongs to H? No need that one. Okay, right. Just what's your aim? Your aim is to prove that AB inverse belongs to H. That's why A into B inverse belongs to H, since H is a group. Yes, this property is associative, closure property, this one. A comma B inverse belongs to H, which implies A into B inverse belongs to H. Now, okay, necessary condition completed. Sufficient condition. Suppose we have a non-empty subset H of A, okay, right, group G satisfies this condition, then we have to show that H is a subgroup of G. Or simply, okay, no need that one. Suppose we have AB inverse belongs to H for all A comma B belongs to H, then we have to show that H is a subgroup of G. Subgroup means, in order to we have to show that H is a group of H is a group. Right. Group means closure, associative, identity, and inverse. So in this case, reverse beta. First, we have to show that identity proof, identity element. Next one inverse. Next, closure property. Next, right, associative property. So A comma B belongs to H, which implies AB inverse belongs to H. Right. So A comma A, I consider that replace B by A. A comma A belongs to H, which implies A into A inverse belongs to H. That implies A into A inverse is equal to how much? B. Okay, right. So here A into A inverse is equal to E. So E belongs to H. So identity element is X in H. Next one is inverse property. So we have A comma B belongs to H, which implies AB inverse belongs to H. That implies E belongs to H. A is equal to E. First one. And A belongs to H. That is E into A inverse belongs to H. That implies A inverse belongs to H. E into A inverse is equal to A inverse. Okay. Inverse property completed. Now, closure property. A comma B belongs to H, which implies AB inverse belongs to H. That implies A comma B inverse belongs to H. Why? Because every element, every non-zero element in H has a multiplicative inverse. That's why A comma B inverse belongs to H, which implies A into B inverse whole inverse belongs to H. Okay, right. That implies AB belongs to H. Therefore, H is closed. Okay, with respect to multiplication. Similarly, associative property. Okay, right. So, if A comma B comma C belongs to H, which implies AB into C is equal to A into B. So, this problem is very, very important. Look at the board. So, here let G be a group and H comma K be two subgroups of G, then show that Hk is equal to set of H into K, where first element belongs to H and second element belongs to K is a subgroup of G. Understood? So, given that G be a group and okay, H comma K are subgroup of G and Hk is equal to set of H into K such that H belongs to H and K belongs to K. So here to show that yes, Hk is a subgroup of G. Just I told no one theorem. Yes, so to prove that H is a subgroup of G means for this we must show that for all A comma B belongs to H, which implies A B inverse belongs to H. By using that property, we have to show that Hk is subgroup of G. So to prove that Hk is a subgroup of G, for this we must show that for all A comma B belongs to right, Hk such that A B inverse belongs to H. That is your A. Only one condition. Don't consider another conditions. Right? Yes. Now let A belongs to Hk. So one element belongs to Hk means any element in Hk is of the form H into K. First element belongs to H, second element belongs to K. That's why A belongs to Hk, which implies A is equal to H1 into K1, where first element H1 belongs to H, K1 belongs to K. Simple. B belongs to Hk such that B is equal to H2 into K2, where H2 belongs to H, K2 belongs to K. Now let us take AB inverse. A is equal to H1 K1, B is equal to H2 K2, whole inverse. Now, so AB whole inverse is equal to, look at this since, yes, right, beta, AB, one second, right, AB whole inverse is equal to B inverse into A inverse, just like that. So AB whole inverse is equal to B inverse into A inverse. Now H1 into K1 into K2 inverse into Hk into inverse. Okay, right. So this can be written as H1 into H2 inverse into K1 into K2 inverse. Okay, right. Don't consider this value directly, we can write it as this one. Okay, right. So AB inverse is equal to, yes, H1 into H2 inverse, K1 into K2 inverse. Now this implies it is belongs to, yes, Hk. Why? Because the first element, H is a subgroup of G. Subgroup of G means, yeah, H1 comma H2 belongs to H, which implies, okay, H1 into H2 inverse belongs to H. K1 comma K2 belongs to K, which implies K1 into K2 inverse belongs to K. That's it. Simple. Right, beta? Yes. Now, since H comma K are subgroups. Right. So this implies AB inverse belongs to H. Therefore, for all, yes, A comma B belongs to Hk such that, yes, AB inverse belongs to Hk. That's it. Therefore, Hk is subgroup of G. Understood? Therefore, Hk is a subgroup of G. Right, guys? I repeat. To prove that Hk is equal to set of H into K such that H belongs to H, K belongs to K is a subgroup of G. Subgroup means, remember this, A comma B belongs to H, which implies AB inverse belongs to H. One condition. Enough. Right. Yes, now, so here, given that this one Hk is equal like this, to prove that Hk is a subgroup of G, for this we must show that for all A comma B belongs to Hk such that AB inverse belongs to Hk. So A belongs to Hk. So what the value of A? That is very important. A is equal to, I consider that H1 K1, where H1 belongs to condition imposed better. H1 belongs to H and K1 belongs to K. Now B belongs to Hk such that B is equal to H2 K2, where H2 belongs to H, K2 belongs to K. Now AB inverse directly. So H1 into K1 and H2 into K2 whole inverse. So AB whole inverse is equal to B inverse into A inverse. Now K2 whole inverse into H2 whole inverse. Now we can like this. Now this can be rewritten as H1 into H2 inverse into K1 into K2 inverse. So many logics are there. Don't consider that one. Directly we can write it as like this. H1 into H2 inverse into K1 into K2 inverse belongs to it. This is only student point of view. Right. So AB inverse, this value belongs to HK. That implies, yeah, first element belongs to H, second element belongs to K. Why? Because we have kind of conditions are there, H comma K are subgroups. Right. So AB inverse belongs to HK. So for all A comma B belongs to HK, such that AB inverse belongs to HK. Therefore, HK is subgroup of G. Okay, right? Thank you guys. Love you all. Have a nice day.